Now they want us to find the tangent line itself and the equation of tangent line and illustrate the scenario with a graph. All right, so the tangent line should be in slope-intercept form. We would have y equals the slope of the tangent line m, which will be 2 is our guess, right? We said the slope was 2, supposedly. 2 for the tangent line slope, x plus unknown y-intercept of the tangent line. So then we just use the one point we know which is on the tangent line, and that's the one that it intersects the curve with, and that is back here, 1, 2. That was the point where we're finding the tangent line slope, because that is the slope of the curve there. So the tangent line and the curve always share that single point, and that's what you'll use to find the y-intercept in these cases. So 1, 2, going back here, y value is 2, x value is 1, and then 2 minus 2 is 0. We see that the y-intercept is 0. Y-intercept of tangent line, 0. All right. So therefore, y equals 2x is the equation of the tangent line. Now for a picture of the scenario. With a little bit of explanation as well. So let's see, 1, 2, 3, 1, 2, 3. Let's just do this. Here's 1. Change my mind. Let's go 1 further over. Scale it by 4 squares is 1. There's 1, 1, 2, 3, 4 more squares is 2. If this is supposed to have the graph of f of x on it, then 2, 3, 4, 5, I'll use a regular scale for the y-axis. Okay. So at the point 1, we know the curve has a corresponding y-coordinate of 2, and at 2, the original curve was x squared plus 1, of course, so 2 squared plus 1 is 5, so we know it goes through here. All right. It also has a y-intercept of 1, obviously put 0 and you get out 1, so there's our quadratic looking something like this. I'm going to try to draw a reasonable quadratic through here. There we go, good enough for what our purposes are. Okay. There we go. Let's draw the tangent line in here. Okay. Good enough. Not as nice as I would like. Good enough. So there's the tangent line. Okay. So that was all they really required of us, but I just want to explain one thing further, and that is what was going on in this process where we moved from secant slopes of 2.1, 2.01, and 2.001 for these respective x values, 1.1, 1.01, and 1.001. So what's happening is this, that if we were to go out here to 1.1, now 1.1 is not that far away from 1. I'm going to exaggerate a little bit in the picture. Obviously, when I mark this as 1.1, that is not accurate to the scale, of course, but just for effect in the picture. Okay? So just forget there's a 2 here for a second. So 1.1, you map up to the curve, right? There it is. And then between that point and the original point 1, 2, we're creating a secant line, and we're measuring its slope. So the slope here was 2.1. That was what we found out, right? That was the slope there. That was m sec there. Okay. So then we took this a little bit closer. 1.1 went to 1.01. 1.01. Let's just say it's there. Of course, it's not really. It's a lot closer according to our scale, but just for effect. So new point on the curve, 1.01, comma, 2.0201 or something like that. And that creates a new secant line going through the original 0.12 and this new point we have here. All right. And that new secant line will have a new slope. And we found that slope to be 2.01, if I remember correctly. Okay. And this is going to keep continuing closer and closer here, right? The next one's 1.001, and the book has 1.0001, which I did not calculate. Nevertheless, you can imagine new secant lines being constructed closer and closer, and thereby their slopes are getting closer and closer to the tangent line slope of 2. Right? That is the idea of what's happening here. So these secant lines are becoming closer and closer to acting just like this tangent line, and therefore the slopes themselves, again, if our guess is correct in this case, should converge to the actual value of the tangent slope, which should be the same as the slope of the curve there, again, by definition.